Hello everyone and welcome to session 11 of the printed circuit board design principle and practices, and this is the last session this semester, and the topics today are interesting as usual. So we'll take a look at schematic predefined special strings in Altium Designer and the PCB predefined special strings as well. Then we will talk about the design variants and templates, and we will try to look what is the best way to design a customizable template for project that includes customizable schematic sheets and PCB layout as well. Then we will do a review for the workflow design in Altium Designer schematic editor and PCB editor as well. And then we will look into 4-layer PCB design projects. So we have 2 projects. We'll do a review and talk about the best practices for implementing 4-layer PCB. And also we can go over how we can convert that into 6-layer PCB. So we start with the special strings in Altium Designer. So Altium Designer implements special strings for the PCB editor as well as the schematic editors, and also the software differentiates between these special strings by special prefix. So for schematic, as you can see in here, the prefix for that is the equal sign, and for the layout editor, the special prefix is the dot. Whenever you place a string in a schematic editor, the only special strings you will see the schematic editor strings. So Altium Designer will filter out the strings for you. When you go to the layout and place a string, then you will see the special strings for layout only, so they will not mix. So in general, on a schematic sheet, the special strings are characterized by the prefix equal sign, as we said. And an example for that, if you try to place a string, and we'll see an example right away after we discuss this slide. If you place a string starting with the prefix equal and use this special string current time, then Altium Designer will read the current time from the system and update the string continuously in real time. If you use equal current date, also this is a special string, and you cannot change it actually. You cannot delete it on a schematic template. So Altium Designer will place the date on your schematic sheet. Now on the layout on the other side, the special string is characterized by the prefix dot, and here you can use dot PCB file name no path or print date. So for instance, in this case, the date will be printed on the layout editor. So the string or the format of the string is also different between the schematic and the layout editors, not just the prefix. Now, if you want to include more than a special string within a PCB string, and the PCB layout string allow for that, you can have multiple special string within single PCB string. All that you need to do is to use apostrophe character for that. For example, as you can see in here, so if you have a PCB file name and then you have the apostrophe and then you have another special string PCB date, also the apostrophe, and in this case PCB file name will be printed, and then you will see next to it PCB or the print date, and you will have space between the two. You can use also space or any other character, special characters. Now since these strings are concatenated, you can use any characters between. So for instance here, you can use character file name equal, and then you have this special string, and then you use special character in here, then print date equal, then you have special string. So let's take a look at these before we move to the next slide. We switch to Altium Designer. So for instance, let's open let's open this. Okay, so let's say we have schematic sheet for this project. We will discuss this project today, but I'm gonna use just the schematic editor. Now if you go to place and select text string in here, now if you click on tab on the keyboard, you will see here properties text. If you open this menu, you will see all the special strings for schematic editor. And these strings are defined in the properties of this schematic document, as we will see. So if you click on time, for instance, place it, and this will not take the time from the system, of course, because this is not the current time parameter. Now, if you click on the free space and go to the properties in here, on the properties you have parameters, and these are predefined parameters in the system, and you cannot delete these. Now look at the time in here. If you need the time to be fixed, for instance, it's 2:06 a.m., this will show up in here. So this is fixed, this cannot be changed. If you need the current time, you need to go to the parameter and change this one to current time. Now this will be pulled up from the system, and Altium Designer will update this in real time. As you can see, it keeps updating. Every time you refresh the document, the time will update. So this is the parameter in the special strings parameters in Altium Designer, as you can see here. So you can have all these different parameters, and these are fixed. You cannot remove them, you cannot delete them, and in order to specify the value, you need to click on the free space on the document, go to the properties, and here when you have an asterisk, that's mean you need to fill in the parameter if you have it placed on the schematic document. Now let's go now to the layout document and take a look at these special strings. Now let's switch to the 2D mode. Okay, so anywhere in the document in here, let's place string. Now let's delete these. Okay, so this is the string. Let's click on it. Now when you click on this here, you have all these special strings or special parameters for the PCB layout. And look how they start with the prefix, with the dot prefix. Now let's say I need the first one, for instance, component counts. Let's see, component counts. Basically, the software will count the component for you and print it in this string. So this is the component count. If I click on here, okay, 108. I have 108 component on my PCB. So Altium Designer automatically count these components for you, and these components actually, this count also exists here. So if you click on the free space in here, go to the properties of the layout, scroll down, you have board information, and look at the board information. You have the size of the board, and then you have the total number of components. You have 64 components on the top, 44 components on the bottom, number of layers, 3 of them are signal and 1 of them is plane, and then you have 18-it, you have all the other parameters. This is like statistical parameters or statistical data about your board. Now I can place another string, and for different reasons, for different parameters. For instance, let's add another string, tab. Then we can change, let's delete this. I need this one, for instance, let's say hole count. How many holes? I have 260 holes. Now I can click enter, oops, tab, and then here we can shift enter. It will switch to the next line or new fib. I can add another parameter now. Let's say net count, and then I have 18-it, shift enter. Let's add bad count. I have 403 bats, and here are the statistics. Now what I can do, I can add, let's say, components count, and now I can add any string in front of it as a prefix for it. You can do that. Same thing in here. Here we have whole count. Let's resize it a little bit so everything can fit. Same thing for the rest. So here I can hit count, and I have add count. Of course, I can put it on any layer. I can put it on a signal layer, or I can put it on mechanical layer as well. So if I activate mechanical layer, I can see it on the mechanical layer. So this is for the variant, for the special strings. And we have seen all that. So next, we need now to differentiate between two things, and this is very important because sometimes it makes confusion. The first one is project level parameters, and the second one is document level parameters. Now, project level parameters are global. Document level parameters are local. What does that mean? When you specify project level parameter, these parameters will be reflected to all the project documents, including schematic, layout, and anything else. Now, when you specify document level parameters, these parameters are at a local scale, and they are available to use within the document itself where you specified these parameters. And we can take a look at that. But the important point in here, the other important point is you cannot use the same special strings for schematic and layout as project level parameters. Basically, the document level parameters is what we discussed in this slide. Now, for schematic, you can use the schematic predefined special strings, and these are document level parameters for schematic. Now, for PCB, you can use the PCB predefined special strings, and again, these are local parameters or document level parameters defined for PCB, and the same thing exactly as before. For schematic, you start with the equal sign or equal character, and for PCB, you start with the dot. Same thing in here. So for document level or for project level, you always start with equal character for the schematic and for dot character for PCB. So let's take a look at this. And here, in order to differentiate, you start with a project, then you create a project name. And the other point in here, project level parameters are flexible. You can set any parameters you want, and these are user-defined parameters, and they will be seen over the whole schematic documents or PCB layout. So, but here for the local parameters, these are predefined. That's why we call these as predefined. These are not predefined, these are user-defined parameters. Let's take a look at that. Okay, go back to the schematic. So here, let's take a look. If we look at the title in here, we can see ou-ivccs.prg, and this title is basically, it's the title of the project. This one is copied. If we go to page number 1, we can see the same title. If we go to page number 2, we can see the same title. If we go anywhere on this schematic sheet or the layout, we will see the same title. So you have two options. For this parameter, you can either define a document level parameter, but you need to update this parameter on every single document. If your project includes 50 schematic sheets, you need to go over these 50 schematic sheets one by one and update this parameter. How? Just click on the free space, you go to the properties, click on parameter, and look for the title and update that. But look, the title here is empty. That means this is not document level, this is project level, and this is the useful of project level parameters. You need to see this parameter in all schematic sheets. I need to see it like the project title. Now in here, you go to the project options, you go to the parameter tab and you define a parameter in here called a project, then title. You don't use title, this will not work. Let me show you. This will not work if you use title, because the title is a special character reserved for schematic. You cannot use it. Schematic document, you need to have project title. Now you define the title. Here you can add any title. For instance, let's add a title called project, and then let's say comment, or let's say project details. For instance, you can specify the value. Now let's say traffic sensor for counting and estimating the speed of vehicles. Okay, so now we have this parameter. Okay, now what we need to do is to create this parameter. Now if you place string and now click tab on it and change the time. Remember, always when you have a schematic, you start with equal. Now enter on it. You see how Altium Designer automatically pulled the data from the project parameter and placed it in here. Now you just need to copy this parameter and have it in your template on all schematic sheets. Now if you go to the project and change this parameter to anything else, let's say let's add anything to it, it's updated in here. You go to the other sheet, it's updated. So it's a global level. It will be updated on all schematic. So this is for the special strings in Altium Designer, and this is just a quick overview about these special strings. Now before we move to the variant, I need to show you where you get more information about these special strings. For the schematic, they are called parameters. So if you search in Altium Designer document for schematic predefined special strings, you will see a list of all these special strings with a description about each one of them. So you have a long list of strings, predefined strings, and you have a description about these, and this is very helpful. And here you can see the special strings for component parameters, because the component is basically a schematic symbol, and it shares the same schematic strings or similar schematic strings, but only 3 or 4 of them are used for schematic symbols, which are current footprint, comment, description, and parameter name. So for the layout, if you search in Altium Designer document for PCB predefined special strings, you will see the PCB special strings starting with the dot. As you can see here for the schematic, they start with the equal, and you have a long list with description of each one. So this is very helpful, and it's nice to take a look at, so you know what you can use. Okay. So let's move on. We will come back to the strings, because next we will learn how to create a template, and we are going to use these special strings during the template, customized template creation. So the next topic is basically the variants in Altium Designer. So when a product needs to be designed and produced as a number of variations of that product, let's say you are designing a cell phone, and this cell phone will come with a different memory size, 32 gig, 64 gig, 128 gig, or 256 gig, 512 gig. In this case, you don't have to create 5-6 different designs for this product, because the only variation you are changing on this design is the memory size. As you can see in here, let's say you have smartwatch, and this smartwatch or cell phone comes with different memory size. So the only the memory chip is being changed for different variations of this product. So you are selling the product with different memory size. So in this case, you don't have to create the same design 4, 5, 6 times just for changing the memory. You can define something called a design variant to avoid the need to create a unique version of the design each time. In practice, a design variant uses the same base design. The only difference is the assembly is loaded with the set of components specified by the variant. So your design is the same, exactly the same, but when you generate the PCB fabrication files, or PCB, specifically PCB assembly file, not fabrication file, PCB assembly file and the bill of material placement file, etc., you select the variant you want to go with this assembly. So here you can see an example on this GIF image. You can see we have two variants for these memories in here. You can use either BGA chips or you can use TSOB chips. So here, by selecting the variant, once you select the variant, we will learn how to create these. No, it's not a big deal. So when you select the variant and go and generate assembly files, you will get either BGA or TSOB based on the selection. So in conclusion, variants determine how the product is assembled, basically. So if you want to define variant, it's how the product is assembled. And in Altium Designer, you can define any number of variations. And again, variations or design variants mean assembly variants, as you can see here. And each component could be configured as one of the three options. Either fitted to the board, meaning this component will be assembled, or non-fitted, and usually they use the character NF, meaning this component will not be assembled, or an alternative replacement part for this component. And it's very common to see a PCB board with so many components on board that are not assembled. And when you see something like that, that means this board is designed to serve different versions of this product or different purposes or different design, and this is very common, and this will save a lot of money because you produce the PCB once and you can use it over or across multiple versions of the design. And this is very, very common and one of the methods to reduce the development cost, design time, and also expedite time to market. So let's and here, before we move, here is also another example. So here you can see the bill of material. We'll take a look at the variant management or variant manager in Altium Designer. And here you have two variants. The first variants for this project, as we can see, we have TSOB and BGA memory. This is the first bill of material. This is the first variant for first bill of material, and this is the second one for the first for the bill of material. You can either go with BGA or for TSOB, and as we will see later on. So let's take a look at these variants in Altium Designer. Okay, so let's go back to the sensor. We'll talk about this design today. I'm going to use it as a reference for explaining 4-layer PCB. So here, as we can see, we define two variants. The first variant, it's called no variations, basically. So everything in this can be defined as fitted. And the second one, which is the assembly status, I defined it like that because in this case there are a couple components I don't want them to be populated or fitted on the board. So how we can define this? It's very basic. You can go to the project and click on variants in here, and this will pop up for you, or right click on the project and click on variants as well. Now here you can see I have the original variation where no variations at all, meaning all the components on the schematic design will be populated, and I have another variant called assembly status. I created this and I specified this. Now these are the components I have on board. These are all the components I have on the board, and now let's take a look at some of the components. This component, for instance, C23, if I double click on it, it will prop, the component, as you can see, and I have a label on the component NF not fitted. This is just a reference for myself. When I print out the schematic sheet, I remember that this component was not fitted on the board. I just add this. Same case for C41. I also have NF not fitted component, and we can see it here also defined as fitted. So I need to define this as non-fitted. Basically, I click on it and I get this list. So variation kind, you need this component to be fitted in this variation called assembly status, or not fitted, or alternate part. So if I specify this as not fitted, click on it, and now this component, when I select assembly status in here, click on it. Now let's take a look. When I select assembly status, you will see how this X comes over. And if you go back to the editor, this is the normal mode. If you switch to the variant mode, you will see that the component that are selected as non-fitted will be X'd with this graphic representation that can be defined. We will see how you can define that. Now, if you switch to no variations, it's gone. Nothing is defined as non-fitted, and everything will be fitted. So let's go back to the variations. This is the variant. Now, what other options do I have? Now I have 1, 2, 3, 4, 5 components that are not fitted in this assembly, in this specific assembly. And in order to do that, I need to select this specific assembly from here. And now let's create a new variant. And let's call this variant, let's call it product model, model, let's say A. Okay, now a new variant is created in here, as you can see. And on this one, let's say I need, what sheet is this? Okay, U8. So I need U8 to be not fitted as well. Okay. And also I need to have, let's take a look, we have C24 on the same sheet. C24. I can define alternate part, or alternative part, or replacement component. So here I can open my library and choose totally different component for this. So devices, you can go and select different capacitor, whatever. Okay, so this component will be used from totally different library. Okay, component, and yep, okay. Now look what will happen in here. Another variation will be added, or another variant will be added. So I have this variant in here right now. So let's take a look. When I click on, let's switch to the variant mode just to see what's going on. When I click on product model, it's X. This will show me this component will be, it has different rotation. I need to correct this rotation for this component, of course. And this one is not used. If I switch to assembly status, now this one is used. This is the original component, and these are not populated. Now when I go to the output job file and generate bill of material in here, I have bill of material. I click OK. I need to generate the bill of material. The bill of material now, you need to specify the variations in here. I say, okay, I need this assembly for assembly status, or product model A, or product model B, or flash size 128 gigabyte, or 512 gigabyte. You can specify that. And now when you generate the mounting files, or big end for the big end place machine, the assembly drawings here and here, and the bill of material, now the Altium Designer will look at what components are fitted in this variation and generate the assembly files and the bill of material based on that. This is the whole thing about variations in Altium. It's very powerful feature, and I used it all the time because when we build, in reality, when we build a product, we have multiple or different variations of the same PCB or the same product. So it's easier and faster to build one design and have variations. And I will show you how you can change these in much faster way. Let's say we need to go to the power and let's select assembly variations and let's see what components are used in these variations. Now look at the toolbar in here. So you have in here edit component variations. If you take this and click on it, and now you will see only this component U3, and now you can change the variation for this component here right away. So you can say, okay, I need this one not fitted. Now if you click on OK, see how you will get the X on it. So where this X come from, how we can change it, if you come to here and you click on drawing style, you will see the drawing style for through-hole component and for surface mount component. So you can specify to use gray box and mesh, or use red cross, or you can use a text and specify, let's say, not fitted, and I need this to be, for instance, as you can see the text underneath it, it's not fitted. So let me remove it, and you can specify the color for that. So we don't want to use text. Maybe you can use text only, non-fitted component, and you can specify all that, or use both of them, red cross, or use a gray box like that. Let's do that for this component, for instance. Okay, look what happened. Now I have NF and it's grayed out with this gray mesh box. Now if I want to change it, you can click again on it, right click, and then you can change this thing. Or the other option is you right click on the component, part action, variant, same thing. Now this one I need it to be fitted. Okay, fitted. Okay, it looks nice. What is how we can make it faster if you have so many components and you need to change the variant on that? So here you can click on this one, toggle part fitted or non-fitted. So you click on it. What parts in this variants in here, selected in here, you don't want to be fitted? Let's say I need all these resistors not to be fitted in this assembly status variant. Basically, once you select this, you can click on it, see how they are changing right away to not fitted components. And if you go now, it's done. If you go now and generate the bill of material for this variant, these will not be on the bill of material. And when you generate the pick and place file for the pick and place machine, these also will not be part of that file. And that is basically how you can specify variants, define variants, and change. Now, if I need to get these back to be assembled, same thing, you just toggle the status of these parts very quickly. Now, let's take a look at the other pages. Now, here I have only one component that is not fitted on this assembly status. Let's see if we have anything on the sensor. Switch to the mode. We have two components that are not fitted. Let's change the mode of the variant into the red X. I like it more. So let's use this. Okay, so these two are not fitted on the MCU. Let's take a look. Switch also here down. You have the editor mode and you have the variant mode. All components are assembled. Switch to the variant mode. On the variant mode, you don't see the nets because the focus in here is on the component. The variant configuration is for the components, not for the net. Here I have two components or two resistors that are not fitted in here. You can see them. Let's see on the storage if we have anything. All the components are fitted. We don't have anything that is not fitted in here. Switch to the mode. Also everything is fitted. So this is how you define variants. And when you generate a bill of material, you go to the job file. Don't forget to select the variants you want before you produce the assembly files. Now, how is this variant also reflect on the layout? Let's go to no variant, and let's for instance, let's change something. Let's go to the GBS module and specify this one as GBS module, and let's specify this as non-fitted. Okay. Not fitted. Oh, okay, we need it on the assembly status. So this one is not fitted. Okay, let's save it. Now, if you go to the layout, now let's look at the 3D model. Look at the GBS model. It's gone. Why? Because I'm selecting the assembly status. If I go to no variations, you can see it. Assembly status, it's gone. And look at this cab also. It doesn't exist in this assembly status, meaning if I need to design or I need to have a version of this product without a GBS module for some reason of the market requirement, then I just need to define variations. I don't need to create a new design for that, and I don't have to populate or solder the GPS module. You can use the same printed circuit board, and you can save a lot of money on that. Or if you go to the variation A, you see, so the GBS module is gone, and this chip is gone as well. If you go back to the original, also no variations, it's the default where you have all the components populated. So this is how you can see it on the layout. On the other, I think on the back side, there are a couple components that are not assembled. Oh yes. So you see all these components are 30, 31, 32, R4. When you switch to this mode, they are not assembled. Basically, they are not populated and empty in this space. So that's all about variants. If you need more details about variants, you can go to Altium Designer document and look for design variants, search for design variants. And always when you try to look into the document, make sure that you are selecting the latest version, because on the list you can see different versions and there are updates all the time when you have a new version of Altium Designer. So 20 you will not see it because I have access to the beta version. I'm part of the beta membership community with Altium Designer. So usually you will see the latest version that is available for public in here, and look for more details about how to use variants. And pretty much that's all you need to know about it. It's simple and straightforward. So let's go back to our slides. So this is for the variant. Now templates in Altium Designer. So how we can where these templates are located, where they are stored, how we can add to these templates, how we can customize the templates. We'll take a look at these things right now. So let's go back to Altium Designer. Okay, so let's close all these and try not to save any of the variations we created. Okay, close all documents. Okay, let me close this project as well. I don't want to mess up project now. Okay, how you can find the directory? You can go to the preferences, and then you have here data management. Under the data management, you have templates, and this is basically the default directory for the templates. So you copy this one and go to the browser, and you will get into the template folder where you have, or you can see all the templates or default installed templates for Altium Designer. You have templates for layout, for PCB, for schematic sheets, for projects, for draftsman, for bill of material, and so on. You have all different kind of bill of material and stuff like that. So now let's start with customizing a schematic sheet template or schematic document template. Let's search for A4 standard. So this is A4. Let's copy this one and let's make a copy of this. Copy. And let's name this, change the name for this document into my A4. Just like that. Now just open this in Altium Designer. Okay. Now when you open this in Altium Designer, on the other hand, let's create a new project just to see how these changes will reflect. So let's open a new project, default project, and add just a schematic sheet to that project. So this is the default schematic sheet as you can see in here. This is just the default. And if you look at the properties in here, look at the properties, you go down, you will see formatting and size, page options, you see sheet size, this is size A, and if you change this one to A4, which is the default template for A4, and this is what you will see. And if you look at the document we edited, this is A4, and this is A4. Let's make sure it's the right one. Properties. Yeah, this is the page sheet size. Okay, same document, but it's sheet size. Go to the template and let's select the A4. Now this will update into that, and of course you cannot change the position for these. These are fixed template, and all of these are document level parameters. And if you go to the properties, look at the parameters, and in order to update, for instance, the number, this is sheet number, maybe number, we should have. So this is not local parameter, for instance, but here these are the addresses. Let's say street number. This will come up as you can see, address 2. Let's say zip code, etc. Country, etc. Okay. So here you can define read, for instance. We don't have parameter for author. You can add these parameters, and the time and date will be pulled from the system, so you don't have to worry about them. For the title, let's search for the title. This is the title, and let's say this. So this is, all these are local parameters, as you can see in here. Now, how we can change these, how we can specify or customize these parameters, how we can change the logo, for instance. Now let's go back to the template, schematic document template. We created the copy and opened Altium Designer. So changing, this is basically an image. All that you need to do to create, you can change the logo in here. Just select the picture and change the logo in here, very easy in here. So if you don't have this image, you can add it by place, drawing tool, and graphic. I need this graphic in here, and then Altium Designer will ask you, okay, where is the logo? So let's select different logo, for instance here. Okay, so we have a logo, for instance, for my company. Yeah, let's change the size, and then you put the logo. It's easy. Then for these, for the address, maybe the address should be global, not local. All that you need to do is to go to, same case for the title. So you can basically go to the project. We don't need it here, but click on these parameters, and instead of title, call it project title. Let's change this to, okay, this is project title. Let's say this is organization. Let's call this project organization, and we need to have these, memorize these, and change the rest for these. So let's see how these will reflect. Now let's save this document. Let's go back to our schematic sheet, and let's change the template for this to our template. So you can do that in two ways. The first one, you can go into the properties, and click on template and select the template from the list, you should see my A4. Or you can go into the design, templates, general templates, and you should see also your template. It's the same thing, it doesn't matter. Now when you get this, do you want to update all schematic sheet? Let's say you have 10 schematic sheets. Yes, if I have 10 schematic sheets, I need all of them to be updated to the new template, for instance. If you need only one, you can update that one. Now also choose parameter actions. I need to make sure that whatever parameters I changed on the original template, I need them to be ported into my current schematic sheets. So I need add new parameters that exist in the template only. Okay, now you can see something changed. You can have, now you can see project title, project organization. Let's add one more document into this project. Okay, we have two schematic sheet, and let's use for here templates, and I need my templates to be used. Okay, here. So now let's go to the project, and now you need to define these parameters. So you add new parameters. This parameter is called, we have project organization, and this called the value, let's say bandwidth. Okay, and let's add another parameter is called project title, and let's call this one project template test. Now when you click on it, see, this one has changed, and this one has changed, and these are global. If you look at sheet number 1, same thing, this is changed and this is changed, and these are local parameters. I had to change them on this sheet, on the first one only, as you can see, but I did not change them on the second one. That's why they are not yet updated. And this is a problem with the local document parameters. Unless you need these parameters to be local, then you can keep them. If you need the parameters to be global, you need to specify that on your template. You need to define your template and specify that on the template, and then you can use this template and use these parameters as global, because by default, as you can see in the Altium provided templates, they are local, or they are document level parameters. You need project level parameters, and for all, usually all these parameters has to be project level, not document level. Maybe what I can do, if I need to add document name or document title, you can do that, and this has to be local in this case. For instance, if we go back to the project we had for the sensor, let's say browse, let's go back, sessions, project, and it's this. So we have several sheets. As you can see, we have power, we have sensor, MCU, wireless, and here I have something called page. Basically, this parameter is called document name, and this will be automatically populated. Altium Designer will read the name you named the schematic sheet and will populate it in here. And let me show you that. So we need to add string text and start with equal. It's called document, I think, name. Okay, and that's it. I did not put any parameter. It's automatically read the document name from here. Now let's place it in here. Now let's copy this same parameter and go to the second document. Just to place the same parameter here, it's automatically updating to the parameter name. Now such parameter needs to be local. Now when I print out my schematic sheets, I can see the title, which is global. This is the project name, and I can see also the document name. Okay, I know that this document is for the sensors, this document for the power, this document for the microcontroller, and so on. So this will be helpful in this case. So here now you can change that. Whenever you are done, you can save your document, and let's say we are changing one more parameters. Let's say, okay, let's add one more parameter, place text string, and let's call this document name. Okay, it's already there, and let's place it somewhere. Okay, let's put it in here. It doesn't matter, or here. Now let's save it, and let's go now to our sheet and click on properties, general, click on the refresh in here. You see that? Okay, update all schematic sheet in this document. Here we go. It came up in here. If you look at the second one, also came up. So sheet 1 and sheet 2, basically it uses the same name. Now if you change the name in here, this will change automatically, update dynamically, and that's for the schematic sheet document or template. Now the same thing is applied to the layout template, bill of material templates, draftsman template in Altium Designer. Also you can go to the default folder, and here you can see the PCB layout, the default PCB layout for A4, for instance. If you open this, it's loading. While it's loading, let's take a look at the rest of the file. Oh, oops, it's locked. Okay, so here you can see you have bill of material templates, and also you have project templates, as you can see in here. Okay, let's take a look. So this is the layout document. It's A4. They have this sheet. They have it on mechanical layer, maybe. Let's see. Oh yeah. Let's see which mechanical layer. So mechanical layer 16. Okay. So they have this sheet on mechanical layer 16. And they have this predefined board size. And they have also this table in here. So now you can change that. Now there are no parameters in that. What you can do, you can easily add a title in here, and by adding string, place string, and remember, when you have a string, you need to start with a dot all the time, and if you don't want to bother, you just can pick up the special string from the list. Basically, let's say you need, let's say, application builder number. This is an automatic number generated in Altium Designer. You have it, let's say, for here, for instance. And this is for the PCBs, just quick. We don't want to spend a lot of time on the templates, but all of them follow the same concept when you prepare concept. Now, what if I want to create a project template? How can I do that? It's also the same thing. Let's close these sheets. Okay, and let's close this project test and this one. Let me show you. So here I have, basically I start a regular project, just regular project, and then in this regular project I go and create a schematic template. It's just one sheet. Then I add it to the project and here, and then I add the PCB layout. I create my own PCB layout. I create my own bill of material, assembly, output job file, specify all these and add them to a project, and then I save this project in a folder, and I put this project within here, this folder. Now when I click on new project, Altium Designer will show me my project template I created within this list, because this list is basically try to update or look for project within this folder. Or you can basically specify the folder in here, change this folder, and try to find the project. So let me show you how you can create a professional project template. Remember in the last session, session number 10, when we talked about flat versus hierarchical? Basically, always try to build hierarchical design, no matter what. This is how you need to do it in reality. So always you will have, this is basically the template I used for my company, for instance. And I created this template, and it's just empty schematic sheets. You have multiple schematic sheets, and you have revision history. I start basically with a parent and 3 children. This is the minimum I need for the simplest design maybe I need to create. So in here, as you can see, I have so many customized parameters in here. And if you look at this schematic sheet, for instance, this one is added. If you go to the properties, show me where this template is. So this is called bandwidth template 11 by 17. And this exists on my special drive for the company. And whenever I update this document, it will reflect into here. I can use the last updated version of it. But here is what you need to do when you create a template to be professional and to have good traceability of the document. You always start with hierarchical design. So you have a cover page all the time, and this cover page will include your sheet symbols, as you can see. These are just placeholder in here. No confusion with that. So these are just placeholder. You see sheet 2, this is linked to this, sheet 3, sheet 4, sheet, and this is also sheet, this is a copy of this. It doesn't matter. And for the revision also I have sheet for the revision, because the revision is very important as well for traceability. Now in addition to that, I will have a label in here, and this is parameter. If you click on it, this is called project title. And when you go to the project and look at the project options, I have a lot of parameters defined in here. So many parameters. And you will see the project title. You need to change this to the project name, because this is a template. When you start a project and use this template, you need to change these parameters, several of these parameters. And then I have also variation or variant special string. So if you double click on it, it's called variant name, and this is predefined variant within Altium Designer, and this is document level variant. Basically, when you select a variant in here, you see no variant, variant. This is dynamic special string, or that dynamically change based on the selection, because I need to make sure when I select a variant and print out my schematic, I need to know which variants these drawing are for. This is very, very important. I need to know when I give the schematic to an engineer, I say, okay, this is the schematic for a variant model A for let's say for 128 gigabyte memory. So this will print it. So the name for this variant is equal variant name, and you can go to the list I showed to you on Altium document on the web in the document, and you will see this variant and it will explain it. That's why it's very important for you to go over all these special strings and see the description of them, because they are very handy. Now on the right side, you will see gray text in here, and this is marked as a draft. When you create a design, the design in the company, as I explained in the first session, if you did not see it, you may want to go back and see it. So basically, you always start. You have a design cycle, and you always start with a draft, and then preliminary stage. And then after that, you need to do design review and go into and say, oh, this is checked. And then you say, oh, this is a release version of it. So you need to specify that. And if you come down in here, you have notes. And I left these notes for anyone want to use this template. Says for design status, you need to select either draft, preliminary, checked, and released. And in order to change the status in here, just double click on it. And this is the design status. And this one is defined again in here, design status. So if I have this on all sheets, whenever you change it in the project parameters, it will change on all the sheets. So this is on the right side. When I print out my schematic, I need to know if I'm looking into a draft version or a preliminary version or its release version. So this is also very, very important. Or when I send it to other engineers to set and call for design review, they need to understand what at what stage or what state this design is. So here also I have an index, and this is a cover sheet, it's index. Basically page number 1, and look how they are numbered. I numbered them. So this I called it 01, 2, 3, 4, 5. If I have 99 page, I keep numbering these page. So what is the benefit of numbering? It will help me to put them in order. So Altium Designer will sort them automatically in here based on the numbering or the alphabet. So if I don't put number, basically C will be the first one, then R, the revision history, will be the second, then these sheets will be the third and fourth, depending on the name. No, I need a specific order for these sheets based on the architecture of the design. So all that I need is to specify a number in front of the name of the sheets. So here, so 1 is the cover page. I know this is a cover page. Number 2, look, I have a parameters called index page 2. If you go now to the project, and here, so I have index page 2, I just say, okay, this is, let's say, MCU, etc. Page 4, I have sensors. Page number 5, I have power distribution, and so on. Let's see. All of them are updated right away. Once I'm done with the design, I can update these parameters and print it out. So remember, you need to define that in the parameters because you don't have access to the template, because this parameter will not be changeable on when you start a new project and board this template. So here you can see I have an index, and this index will give a very good overview about my design. And then on the right side in here, you can see I have my own box here in the template, and this template shows a specific information. It's important to me. It shows the title, it shows the page name, it shows the date, time, drawing number, revision, variant, number of the sheets, and the size of the sheet, the address, it shows the logo, it shows if this is confidential or not, and it shows also where this file is located. And on the top of that, I always show the 3D model from the top and the bottom. Let me show you an example for that. This is for project for the university. It has nothing to do with the company. I have different template for that. And you can see here, this is for the sensor. I have 3D model for the top side and the bottom side. And this gives a very good overview about the final shape and size and look of the PCB as well. So you can see that. So on my template, I specify a dummy picture in here, and all that you need is to change it. So 3D model, top view, double click on it, and then you can select the image. After you generate the layout and produce the 3D file, you can generate the image. How you can do that? This is very easy. We can take a look at it. So let's say this project is done, and you have the layout for that. Let's open it. So two ways you can do that. Basically, you can come here, take snapshot for this, flip it on the other side, Control F, take snapshot, save these images, and go and import them. The other way, you can go to the output job file, and here you can create documentation output. You can add 3D print in here, and you can specify this, and you can print out the 3D view of this. So let's say, okay, so another video. So you can come here, take snapshot of this, just take a picture, so do the other side, take a picture, or you can print it out into a PDF file and also take snapshot of that. Several ways you can do that and save it. All that you need then is to, let's go back to the Altium Designer. It's to load it into your project. And when you load it into project, make sure to check on the embedded. If you don't check on the embedded and you deleted the image or you change it to the directory, then you will lose the image. When you do an embedded, basically Altium Designer will take a copy of this image and embed this image into the project file as well. So one for the top, one for the bottom. Click on this one for the bottom and take an image as well. Now, the most important part of this template, as you can see. Now, still talking about the cover page, and the cover page should show you the hierarchy of the project and how everything is connected together in here, because we need to add the connection now between these when we start designing, and also we'll give a full information about the project. And here you need to use these boxes. Look, so for the notes, mark not fitted component as infit. Basically, you can copy this non-fitted and place it over the non-fitted components as a reference for you. Now, set project parameter in project options parameter. I'm giving information for whoever is gonna use this template to set these parameters under project options parameters. You need to set these parameters. Then design status, you need to change it as you progress with the project design. Then use the following design consideration notes to mark the design. So you have 6 design consideration. The first one, it's write critical design notes. This is for schematic. Basically, you copy this and then you change the content of it. You know, this is color coded. Red is for schematic critical design note. Blue is for the layout critical design note. Green, this is for just information, general information design notes. Now you have cautionary design note in this color, you have debugging design note if you have a software in this color, and assembly guidelines in this color. And you can add more if needed. Now let's take a look. Let's go back to the OU project in here. So as you can see, this is very old template. Comparing to this is a new template. The one I was showing right now, this is a new template. And I learned a lot during this time, so I updated this template based on what is needed for the company. Now, when I was working for University of Oklahoma, so this is what I used, and this is what I created for University of Oklahoma. As you can see, my old office, OU logo, and information about it, and that's all needed. We don't need to have a special revision or special variant or special part number or etc. So this was very sufficient at that time. And here you can see I have also the title, project title, and this project title exists in the project options parameter, and this is the only parameter, global parameter I have. As you can see, I have, let's close this one. Okay, hierarchical design, as you can see in here, and how everything is connected together, what signals are ported from one side to other side. And I told you, try to have the flow from the left to the right. As you can see, this is the power. I put it on the left side because all the signals are going from the power, let's say, to the microcontroller, and I have some control signal going back from my microcontroller to the power stage to enable load switches. I will explain this design in a bit. Now I have a wireless module for Zigbee. I have sensors. I have data logger in here. I have localization module, the GPS module, and you can see what signals are boarded from one side to another. And here I have, as you can see, it's not like draft, preliminary, checked, not checked. You can see that it's checked, dash, who checked it. You have the initials for the one who checked this page specifically, and you should have it on every single page. Let me close these, or every single sheet. And let's close this. Let's close this. And now we will go to page 1. You can see I also have a reference in here. Now on the page, as you can see, here I have this information as well. I have the 3D model populated. I have notes. And when you go to sheet number 1, on every single part of the circuit, you can see there is a text that explains what is this section about. So basically you can come and try to look at this. Oh, okay, this chip is ADB 5091. I can search for it. Oh, this is energy harvesting chip. You don't have to do all that. If you are taking a quick overview about it, I need to understand that this is a load switch without searching for the part number and trying to understand what is this component by looking into the bin. No, if you have description text on the top of that, this will make it very easy or readable design for any engineer. And then, as you can see in here, I have these commentary blocks. As you can see, this is for schematic. This is critical node for schematic. Use 10 kilo ohm pull-up resistor for serial data and serial clock. This is very important. I need to have it. Here, these are for the layout. Everything in blue is for layout. C1 can be used as bridge to connect the board ground plane without using a via under the device package. Now, place the capacitor between battery bin and VCC close to the gauge because we need to close the current loop in here, make it as small as possible. And you have all these nodes. When you design schematic, you can put them. When you go to the layout, you can have a reference when you do your layout to make sure that everything is right. And here on the schematic, as you can see, these are the voltages at these pins based on the design, etc. So this is, you need to do that for every single design. And look how easy to read this schematic, because you have a reference everywhere. You have color coded the nets. Also, you have a description for every single or for the main components you have or main sections you have on the board. Let's go, for instance, to the sensors. Here I have one sensors, I have explanation, I have documents, it's magnetometer, accelerometer, it's checked, and I have this in here, and so on. So microcontroller, again same thing, I have oscillator in here, I have power bins, I have power filtering embedded controller, and I have the interfaces with so many comments everywhere. These are very, very important. Here, for instance, these pins connected to ZigBee GPIOs for upgrading microcontroller firmware over the air in the future. So you need to understand why these are there. Here, I have jumpers in here. B solder, B13, BA13, and BA14. These pins before using the debugging interfaces. So this is yellow, and yellow for debugging, as you can see. And same case for the rest. So it's just we want to show an overview about that, and we will talk about this design in a second. So let's go back to our template we were talking about. So here is the template. So I have the cover, again, I have a cover page, and I have these sheets ready. And in the same time, I also have a layout, as you can see, and I set the variant, but nothing different. So this is my layout, and I have special template, of course, for my layout. Let's see if everything is active. Yes, everything is active. And I have also a special classification for the mechanical layers, or special naming convention for the mechanical layer based on the use. And this is by default, this layout, as you can see, is for 4 layers. I have another layout for 6 layers, another layout for 8 layers, and these are templates. You don't have to design stack layers at the beginning and put that. No, they are pre-designed. Now, if you want to change the layer stack, you can change it through the design, but you don't have to start that from scratch, because you have something, or you have a point you can start from. And this will be very helpful and will save the time for the engineers working in the company. So you can see we have template for the layout, you have a template for the bill of material, template for the assembly, template for the drills, template for the output job file as well. So all these are pre-created. Now, in order to run the job file, you just select the file you want to generate and just click generate the content, and all of these will be automatically generated. You don't have every time we create a project to come and set the documentation output, assembly output, fabrication output. No, everything is preset and configured according to the standardization process of the company, of your company or the company you are working for. Now everyone will use this template and generate like procurement files or documentation for a project. All of them will be standardized. They will look the same. They have the same format. They have the same mechanical layer usage, and so on. So this is very important when you work for organization and you need to harmonize with the rest of the team. And this is how you can create that. So how we created that, basically you you modify the schematic sheet and then add it to the project, and then save this project in the project folder or directory, where you can, when you open a project, you just open this project wherever you have it. It's very easy and very straightforward. So this is for the template. Let's close this template, and that's all we need to know about it. It's not complicated, it should be simple. So now let's go back to the slides. So design a fully customizable project template. We talked about this. This is very important when you go and work for a company or establish company. Make sure that you standardize the process, the design process, starting with the templates, of course. Now let's talk about the project, 4-layer project. And before we do that, let's do a review for the schematic design flow, because this is what I use all the time when I create a project. So as we said in a couple sessions earlier, so always you start from the design concept and specs. You need to have specifications for the project you are designing. You create the project, you add schematic sheets, build, design, hierarchy, and again, if you have a template for the project and schematic sheet, you don't have to create these. You just open the template and use it as a new project. Then you need to build the hierarchy. The hierarchy, now you have pre-built hierarchy in your template, and now you need to populate these schematic sheets. If you need more schematic sheets, you can add to it, and then you try to connect everything together on the cover page. Then you search for components. If you don't have a component, you create component, place them, wire the component, place nets and directives, do the annotation for the components. Don't forget to number the schematic sheets, set up the project options, and compile and verify the design. And then you need to sync with the layout. On the layout side, we said we start by defining the board shape. This is the most important part. Don't board the component before you define the board shape and define also the grid. So then you configure the board properties, as we said. Then you go to the board origin, specify the board origin. You set the board origin. Then you would specify the design rules and transfer now the design from schematic. Now, in order to set the design rules, you need to transfer the design from schematic, because you need to pull import the information about the nets you have and the components, etc. Then you start placing the planned component placement before you place the component. And again, always you need to plan that. And component placement is very critical, because if you don't have proper component placement, you might not be able to route the board, or you might need to have a bigger size for the board to able to route it. So you need to plan in advance. You don't want to just move the component, place on the board, try to do routing. No, try to find the minimum cross between the component and try to place the component such that they can be easily routed. And you might at some point to go back to the schematic and try to swap some of the nets to simplify the routing on the layout. And also, you need always to start placing the connectors that interfaces with the outer world or interfaces with the user, because usually these connectors are on the edge of the board. You need to have them placed first. Then you look what is your core component. If you are designing a board with microprocessor or FPGA or microcontroller, the microcontroller, microprocessor, these are the core components, because they are branching everywhere to all the surrounding peripherals or components. So start with this component, place it in the center of the board, and see how you can distribute the rest of the component. You don't have to keep it in the center, but this is your core component where everything will branch to. So start with it. Then position component, plan the routing before start routing. Now, if you have differential pairs, for instance, differential pairs, you need to have links matching. To have links matching, you need to keep enough spacing around these differential pairs so you can have a space to links match them. Or if you don't do that, and try to route them directly and route so many wires around them without leaving space. And when you come to the point where you need to match the links, oh, I don't have space for that. Now you need to do the layout again. So this is very critical. Start with differential pairs. Make sure to keep enough space around them for links matching, or you might match them at the beginning if you want, so you know what space you need. Then start with routing data buses. So data buses should be routed together. They should not be separated. There should be no discontinuity in the routing. Make sure to route them all together because they have the highest priority. Then you can route the rest of the component. And as you can see before, when you plan routing, you need to design the layer stack, fan out the pins, start routing, refine the routing, you keep refine the routing, move the traces, make them move together. Then you add the copper pools. If you have ground, you need to add ground copper pools. Maybe if you need to have power copper pools, if you have split planes and so on, then you can add via stitching. And we talked about via stitching, I think, in session number 7 maybe, and number 10 as well. And we talked about how you calculate the spacing between the vias based on the wavelengths. Then you need to adjust the designator and place any other node, run the design rule check, and make sure that you don't have any error. Do a design review, then you generate the manufacturing and assembly files. Now let's take a look at the 4-layer PCB project. This is project. This is very small board. This is a sensor for traffic, intelligent traffic monitoring, and you can find information about this sensor in like really detailed information if you go and search bleed dissertation, and it will come at the first result. This is my PhD dissertation, and inside the dissertation you can download the dissertation, and I think which chapter? It's introduction, background, consumption. Okay, sensor design and system integration is chapter number 3. So in this chapter you will find full information about the first generation of this sensor and the second generation, and also you will find detailed information about the workflow, how you really design a product, and selection criteria for the component. Here you can see candidates, selection criteria, how we select these, how we select the other component, how we do integration and so on, how we calculate all these information before we put the design on a board. So you have full information. If you need to do that, you can take a look here. For instance, selection criteria for magnetometer and accelerometer. So I came up with 2. I found the best 2. Then I start comparing these characteristics and specification for the sensor and look into what are the specifications for the sensor I'm designing, which one will fit best. And also the price factor was an important point. As you can see, this one is like $1.5 for 1 kilo unit, and this is $4 for 1,000 piece. And there are other factors for wireless communication modules. As you can see, after a long search, I found the 4 best candidates in here, and then I start looking into these characteristics, and these characteristics are selected based on the product requirements, of course, because sometimes you need speed rate, data rate, I need power consumption, I need for instance distance, how far, and I need for instance the size, the cost, supported protocols, and etc. So I have the major points to compare, and then I select based on the requirement of the product and so on. So take a look at this. It's very long. I think chapter 3 goes over the selection criteria and the design procedure for this in addition to calculations. And here you can see the final product. So this is the sensor, and this is basically 10 cents This is very small, it's just 10 cents. And this is solar cell because this one has energy harvesting and can charge a battery. There is an internal battery, lithium polymer battery, and it's charged from the solar cell. And this also has inductive charging. And this is basically the charging circuit for the inductive charging. And this is the antenna for the inductive charging circuit. And you have some software information about the algorithms and the protocols as well. So after that, it's now mathematical modeling and analysis and etc. in addition to the applications. And if you go to the bottom, you can see we talked about this one design process in I think in session number 1. In session 1 of this course, we talked about this and we explained the process here in details. Now, this process is basically the process I followed in designing this sensor because I had the knowledge on how you design product as a product, not as just mature design by a student. So I followed this project and it's very well explained and applied in this dissertation. So take a look at it and it will be very helpful for you as well to learn how you create a project with more details. So this is the sensor. Basically, the sensors include a couple of peripherals. The objective of the sensor is basically so we started from the objectives. And let me tell you the story how we started this. Basically, the customer, who is Oklahoma Department of Transportation, this is a state agency, came and asked University of Oklahoma, okay, we need to design a sensor that can count vehicles, estimate vehicle speed, vehicle lengths, and do vehicle classification. And the design objectives are we needed to have low power, can operate on a battery, very small size because we want to place it on the road and we don't want it to be big. And also we need it to be installed very easily without any intrusive work, meaning they don't want to dig on the road surface because blocking a highway in United States to install any equipment or any sensors costs hundreds of thousands of dollars. So you need to make sure that it's not intrusive. And they provide a lot of information. And basically, after that, we had to put design objectives, and they are in the dissertation. You can read about them. And the design objective, they need something very cheap because this sensor will be scaled in 100 and 1,000 sensors and distributed everywhere, and they are connected wirelessly. And the setup, they don't need to have any intrusive. They need non-intrusive technology. Very easy to install. They don't want to even dig a hole in the road. Just place it on the top of the road. They need also energy budget. This sensor should operate for so long time on a battery. They don't have to go and change a battery because the labor cost is very high. Driving, if you have a sensor distributed all over the state, it takes very long time to drive all over and try to swap batteries. It makes no sense at all. So then the performance, it should have good performance and able to operate in real time. If you have a high traffic volume, you need to be able to count all these vehicles and give reliable data. And then reliability is very important because they count on the volume, travel time, speed to give traffic information, especially if you are driving from point A to point B. They count on these measurements to estimate the travel time and tell you if there is any congestion on the road or not. Lifetime also, they should be usable for a specific amount of time. Portability also, this should be portable, etc. So there are so many design objectives, and these are the requirements we talked about, and we generate restrictions as we described in session number 1, and then we do feasibility analysis. So we did the feasibility analysis and came up with this sensor, which was part of my dissertation, PhD dissertation. So these sensors include, as you can see, based on the requirement, and here is where the engineers come, engineers rule come. So you have transceiver for communicating data to base station. You have a GPS module for localization and time synchronization. You need to know where the sensor is installed And also you need to have the time on the GPS for time stamping. So when you detect a vehicle, you need to know what is the time for this detection in very accurate scale. Then you have, this is the antenna for the GPS module. Then you have embedded controller, which is the core of this board. As you can see, it's in the center of the board. You have connectors to connect battery and connect energy harvester in here. You have power management. You have serial flash memory and micro SD card for data logging. You need to log the data. If you don't have wireless connectivity with the base station, you need to store the data locally. And whenever you have a connection, you can transfer the data to the base station. You have a sensor, magnetometer, and accelerometer in three dimensions. You have other peripherals, voltage regulator. On the back side, you can see you have also other components. And this is the board as I showed you in seconds. This is the GPS module. This is the antenna, connector on the edge. You have microcontroller, you have other units, and on the top side and the back side. And you can see this is 1 cent. So 1 cent is basically, the diameter for 1 cent is 19 millimeter. It's 3/4 of an inch. So it is really very, very small. If you see it in real, it's really very, very small. It's like you can put it on a finger, on 2 tips of the finger. So it's very, really small. So let's see the design for this. Where is it? So let's take a look at the design. So this is a project, as you can see. And I have a variant in here because I have some components are not populated, as you can see. But let's start with no variant. So on the top, basically you have the cover sheet. On the cover sheet, you have the notes, 3D models, and also you have the hierarchy of the design. And you can see how everything is connected. And if you come closer into this box, this is very important. And we learned how to do this in the last session. So here, this, of course, you added from here is sheet symbol. So this sheet symbol, you can see the name of the sheet symbol. When you double click on it, the designator, I name it as Zigbee module. It's descriptive name. I know now this sub module is for the Zigbee module. And here it's linked to the sheet that is named wireless, because the Zigbee module is part of the wireless communication and it's on separate sheet. So we have a modularity in here. I can reuse these. If I create another project that requires the Zigbee module and I want to use the same Zigbee module, all that I need to do is to copy this schematic sheet, make a copy of this, save it somewhere else, and reuse it. Look, it's very simple and everything is very well organized and it's ready to be used. It's very simple. So this is very important. And these are the inputs and outputs connecting with the microcontroller, which is the core component. Then I have here energy harvester, which harvests energy from those solar cells, use it to charge a battery and also supply the system. In addition to that, I have a fuel gauge to monitor the battery. I have voltage regulators and load switches to switch on and off the loads based on the available energy. So, and here you can see how everything is connected, and you have connectors and terminals, and I changed the color of the net. And remember how you can change the color of the net. It's very easy. You just select from here and change the color for the net, and this will reflect. And we talked about it in the last session as well. So then we have the microcontroller where everything is connecting with. It's in the center. If you go into the microcontroller, we can see the connections and the net and the boards. We talked about the boards as well in the last session. So, and the rest of the components, we have the magnetometer and accelerometer here. This is the magnetometer, accelerometer, and we have 2 non-fitted components. So why these are non-fitted? And you can see in here. So do I have description? No. Basically, if you fit these, I think it's in here. The picture is missed. Oh, here. So I have description in here. C41 and C23. If you are using this sensor, these should be non-fitted. If you are using this sensor, because they have the same footprint, then you need to put 100 nanofarad in here. So this configuration that I have in an assembly status is basically for using this sensor. Okay, so we can go to then we have the serial flash or data logging circuit. I have a micro SD card with ESD protection, I have flash memory, serial flash memory, ultra low power serial flash memory. And then the last one is GPS module. I have a GPS module in here. And this is the connection. Now, something we forgot to mention in the last session, which is using the harnesses in here. This is the harness. So what is the difference between harnesses and ports? And again, with harness, you can combine multiple nets into a harness. And this you can look into it as a bundle. It's like just a bundle. How you can create a harness? So you can go in here. First of all, you need to add harness entry. Or sorry, you need to start with the harness connector. So this is the harness connector. You place the harness connector first. Once you place the harness connector, now you can place harness entry, which is from its name, it's the entry of this harness. And then you need to place signal harness. This is for the output. And you need to place a port, just a regular port. Now look what will happen to the port when you connect to the signal harness. It changes into a harness port now. And here, all that you need to use is just regular wires in here. Nets, just nets. And now you can add nets to these. Sorry. Place it layer. And then you need to change the port name. Let's say port, whatever. Let's say this is data bus, for instance. Okay. Resize it. And then you need to change the harness type in here. And this harness type is basically how it's determined by the system. Let's call this one data, let's say memory. Okay. And we don't need to show this harness type. And then you change the name of these harness connection points. Let's call this one data bus 0. This is data bus 1. And this is data bus 2, data bus 3. And if you want to change the label name, you can change it in here. So we can resize this in here like that. Connect. Okay, the harness is ready. That's all you need to do. So if you need to specify the directionality, let's say this is output, and this one is designed as data memory. Now you need to copy this. Let's say this goes also to the storage, for instance. Let's put it in here. Okay, so this connect with different net labels maybe, because it's on different memory or the same net labels, but it has the same thing in here. Now the first one on the GPS, the second one on the storage, I have, assuming I have two data bus needs to be connected. Now I go to the main page. So the first one on the GPS, the other one on the storage. So the GPS, what I need to do in here, I also need to create sheet entry. Add a sheet entry. Now what I need to do, look, this is the important point. Double click on it, and harness type, it's data memory. What is the name of this? We can use the same name if you want, or if you will. You can use data bus, for instance. Data bus. IO type, is this output or input? You can specify that. Now the other one is on the storage. It's in here. Basically, again, sheet entry. When you double click on it, the harness type will show you whatever inside this. So this module has this harness types. So it's this one, and it's data bus, and now I need to use harness connect, signal harness, and connect these two together. So what is inside the signal harness is basically 4 traces. The first one is named DB0, DB1, DB2, DB3, and these 4 signals, DB0, 1, 2, 3, going from this module into this module and connecting on the other side with DB0, DB1, DB2, DB3. So the connection between this and that depends on the name in here, the harness name, 1, 2, 3, 4, and this has to match. So DB0 will go with DB0, no matter what is the net name in here. This is how the harness works. Now, how can I do this with boards? Basically, you use 4 boards. It's exactly the matching for this. Let's copy and paste. It's faster. Is this? Let's say if you have these, let's delete this and call this DB0, DB1, DB2, DB3, and let's specify all these as properties. These are our output, and copy them. Go now to the other page, remove the harness, or place it in here, and these now are input the other way around, because output from the other side, they are coming input from here. Now these are the same, but now imagine that you have a data bus with 24-bit or 16-bit. You need to have 24 one of these rather than having only one wire. And now when these goes out, you need also to connect them. Now you should have 4 of these boards. You need to get from here to here 4 boards instead of only one harness signal going in here. If you have 24, oh, this will become huge. That's why. So you can look at a harness as a bundle or as a tube, and inside this tube you have so many wires. And this is it's very useful when you have a complicated design. So let's remove these and go back. So basically this is the schematic, as you can see, how everything is organized, how the comments are placed around the components, and I have net color. Also, we say how we change. It's very easy to change the net color in here. This one will be very helpful when we go to the layout. Let's open the layout. Of course, we are not going to create the schematic from scratch today because we learned how to do that, of course. So if you click on it, okay, we'll take a look at that. So this is the schematic. Basically, everything is built based on the data sheet and the application notes. So the placement of these components, the surrounding components, what you need to do is to go to the data sheet. And in the data sheet, there are specifications about the design you need to study, and you need to understand the component you are using. It's not just you pick a component, place it, and connect without real knowledge about the decoupling capacitors required for this component, the placement of the surrounding component, and so on. You need to go into the data sheet and understand the component in details. For instance, this component, let's take this one. Okay, or let's copy this. Let's search for it. So this is ultra low power supply voltage supervisor. You look at the data sheet, and here you can see there is application diagram somewhere in the data sheet. Let's scroll down. In here, show you how you can control typical application. You always see it under here. And here you can see the design results for specific voltages or specific model. And most importantly, if you go down, you have layout guidelines. And these are also very important. In addition to the schematic guidelines, you have layout guidelines. So they will tell you need to place bypass capacitors 100 nanofarad as close as to the VDD bin, and this spacing from here to here should not exceed 5 millimeter. And this is how you place it, and this is the distribution, and this is a very simple component. When you talk about BGA or FPGA or complex microcontroller, you might have like 20, 30, 50 decoupling caps around the component, and they have to be placed in very critical positions. So you need to read the data sheet and the application note about the component you are using. It's very, very important. Don't place component before read the datasheet and application note about the component to understand what is the best way to use this component, to route it, to place it, to make it immune for noise, and etc. So once you create schematics similar to what we learned, we transfer that into the layout in here. As you can see, on this layout, we have 4-layer PCB in here. So let's hide the layers. Let's keep the components, and let's hide the mechanical layers as well. Let's hide the bottom layer, and this is what you will see on the top layer. These are the components on the top, and here you can see the component on the bottom layer. And now let's take a look at the top layer. You see, you have top, you have the components, and all the empty spaces, basically they are filled with the polygon. Let's select the top layer, let's click on it somewhere. So basically this is a ground, as you can see, and this is a top ground. This is polygon. Now let's hide the polygon. If you go to Tools, Polygon Poor, Shelf, I have 9 polygons, as you can see. It's cover poor, shelf. And let's hide the component on the bottom side. This is what left. When I started the routing and finished the top and bottom and all the layers, as you can see, let's see, this is power and this is pure power, and this is the bottom. These are the routing. You see how they are simple? There is no complication. You have so many components on the board, and the module is very small. It's really, really small. It's like 2 cents next to each other, and the routing is very simple. So what is the secret behind that? It's the placement of the component. How you plan placing the component on the board. This is the secret. And you should not route any ground signal. Ground signal should be connected into vias, and they should be connected on the bottom layer. And how you can do that? You just fan out these ground paths by via and wire. Don't try to route the ground from point to point, point to point. You will complicate the board. Just next to every single ground pad placed via, and forget about it during the design, during the routing. Now, once you are done with routing the main component, last thing you need to route is the power traces and the ground. This is a general. Sometimes you need to route the powers first, but in general, you just fan out your ground and power pins into vias, and now you know you have a power plane and you have a ground plane where you everything ground and everything power will connect together. So you don't have to worry about it. Now you can focus on routing the rest of the traces, and this is very, as you can see, it's very simple. Now once you are done, you can go and create the polygon or the power, the cover pores. So let's go Tools, Polygon Pores, Polygon Manager. Let's take a look. So on the top layer, let's say I have on the top, I have this ground pore, and it's shelf right now. Let's remove the shelf for this ground pore. Okay, and here we go. So let's remove the bottom. As you can see, all these spaces are filled with ground, and look what I have. I have via stitching as well for the ground in different places around the board edges here, and I have a shielding as well here around the antenna, and everything is going to the ground. Let's take a look at the bottom side of the board. This is without ground. You look at these empty spaces. I can put the ground on the top layer as well. So tools, polygon board, polygon manager. Let's take a look. Where is the ground for the bottom layer? Top bottom ground. It's shelved. Okay, let's activate this. Okay, here we go. Filled all the spaces. Now this area, this is where the antenna is, and they will tell you on the data sheet you should keep this area, you should not put the cover in this area, otherwise the cover will attenuate the signal on the antenna, because if you recall the last session, the cover is ground, and this ground will contain the electromagnetic field around the antenna and reduce the signal strength, and we don't want to do that. Basically, we need to radiate in here. So this is the bottom side, and you see how everything is filled, and you have the ground vias everywhere in here. Now let's take a look now at the power plane. Here is the power, and we need to show, because also they are polygons but for the power. Tools, polygon board, polygon manager. Looks like I shelved the ground as well. I don't want to shelve the ground. Let's see. So these are on the power layer 1, 2, 3, 4, 5, 6. These are different power. Let's see. This one is system. This polygon is connected with the system, and we can show it. I change. Okay. So basically, this one is for the system. You see, it's polygon, a small polygon board. But this one is connected with, I have supply called system, and then I have supply for the micro SD card. Apply, and this everything is connected here. So basically, I can come here. If you look at this, so my VDD micro SD card. If you show the top layer, maybe they are on the bottom, and I need the bottom on focus. Here you can see it. So this is the micro SD card in here. So this is the power supply for the micro SD card here and here and here and here. So I connected all of them with a big area of copper, and this basically will reduce the impedance of the power in here, and also will provide shielding for the noise, because you have now VCC or power signal and you have ground signal. So you have a strong coupling, and you are creating coupling capacitor between the ground plane and the power plane in here. But in most of the cases, when you design a board, you will have multiple power supply rail. So it's not, the power plane is not only used for a single supply like 3.3 volt or VDD. No, in this case, we have VDD, you have power supply for the micro SD card, power supply for the GPS module, and they are different. So GPS module running on 1.8 volt, micro SD card running on 3 volt, microcontroller running on, let's say, 3 volt, and the other module running on 2.5 volt, and so on. So you have multiple relays, you can distribute them on the power plane. So let's go back to the tools, power for polygon manager, and let's show the rest of the power. So I have power for the RF. This is basically for the Zigbee module. I have power for the GPS module, and these all on the power. I have power for the battery. This is the supply coming from battery, and I have power 3.3 volt for the system. Everything is connected to this. So I have all these power rails. Okay. And let's take a look at the power now. And let's hide the bottom, keep the power only. So this is the distribution of the power, and this power is basically on layer number 3. And this is power layer. So here you come closer, if you click on it, so this is VDD for RF, and this connect basically the Zigbee module, wireless communication, and this is basically for the 3.3 volt system, and you can see the vias connected with this. So this 1, 2, 3, 4, 5, 6, and these vias are isolated, as you can see. So 7, 8, these are connected here, and you can see the power, this one, that's why I'm branching in here. This one, no, this one is different. Now this is for the system, and you can see the power for these lines. Now if we show the top layer, where let's say this is connecting to the bottom here. So you see these GPS, how they are connecting in here and in here, and basically this is how they are connected on the power. But on the top side, I only have a VS, and then fanning out into connections. This is a 3.3 volt system, so it fans out in here. Looks like okay, and then connect on the bottom layer. You see, just fan out and connect. Here, fan out and connect to the plane, power plane. In this case, I don't block the place in here for other traces. I focus to connect my signals on the top and bottom layers, and my power signals and the ground goes into the power and the ground planes. This makes the design routing very easy. It's way easier than try to never route the ground and power planes on a signal layer. Just fan out them into VS as close as to the pins, and then they connect on the power plane layer or specific layer. So here again, so micro SD card, look at the micro SD card in here. So I have branch in here, you see, it's branch in here. Just, I don't have to connect this one with this one. No, they should not be connected together. Just to branch them here, again here, you can see that here. And then on the bottom layer, so how nice it is, everything is connected together. This is how you should branch everything. So let's take a look now on the ground. Now the ground is plain. Everything is ground in here. Everything is ground. And these are not connected because you see, because this is negative now, because this is plane. Here they are connected. This ground, you can see these X's. Everything is X is connected to the plane, and everything you have solder mask around, these are not connected. And here it's not filled. There is nothing at all in this layer. Now let's take a look at the 3D model for this. And let's hide the component. We do want to show component body, orthogonal. And then let's switch to single layer mode on. Okay, this is nice. So this is the ground plane, because the ground plane is showing in here. This is basically the ground plane. It's inside the PCB. So we are only showing one layer in here. Let me show the other layers as well. Okay, so when you switch the layer in here, you can see this is the top layer. This is the ground, the layer underneath. This is the power, and you can see how the power are connected inside, and these are the VS connect with the power, and these are isolated from the power. You can see that very clearly. And this is the bottom side. This is the bottom of the board. This is the lower layer. You can see it's very, very nice. So let's put it vertical. So this is the bottom layer, and this is the power layer. You can see how everything is connected. Ground, it's solid copper layer, and here we have keep out layer for the antenna. We need to make sure that there is no ground underneath the antenna, otherwise we will kill the signal. And we have the top layer. This is the single mode, and this is very, very good visualization of the board. So let's switch to turn it off, single layer mode, and we can show the color by the layer. So this is the top. Your configuration, show by layer. This is component. Okay. Yeah, this is for 3D. You can use it, and of course, you know, you can space the layers and look inside. You can get inside and see how these vias are connecting together. And to space the board or scale the board, you can scale them from here. And here you can see how everything is connecting. And to make it more clear, go to the core and change the change this. Now we can see even more. Let's go change more. This do configuration, make it transparent. And you see this area where we don't have a cover for the antenna. underneath the antenna. You can see it very, very clearly. So there is no cover over all the layers. It's keep out area and no cover at all. And it's empty. We need to make sure that nothing will attenuate the antenna signal. And here you can see the vias, how they are connecting into different layers. To the ground, we have the ground plane in here. So for instance, you see these are connected to the ground, but this one in here is not connected to the ground. These are not connected to the ground. This one is connected to the ground in here. And this basically going all up, down, 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 down. And then it's not connected on this layer. And then going down to the bottom layer. This is good for visualization to explain the board. Now, once everything is done, you have the output job file, and you can see in here. So you have assembly, drawing, fabrication files, and also we talked about these. Once you generate these, they will come into here, and you will see all of them. The Gerber files, NC drill, pick and place machine, and so on. Now, this is just simple example how you can design with 4-layer PCB. Use the top and bottom layer for signal and use the inner layers for ground plane and power plane. And try to separate or use split plane for your powers. If you have multi-rails, you can use regions for different rails as well. Now, the other nice project you can try to look at is if you want to start with 4-layer PCB, my advice to you, because some students and engineers ask me, okay, we need something to practice after this course. So the students attending this course at University of Oklahoma, they already have home assignments, they have projects they are working on. But for the other people watching this video on YouTube, they are asking, okay, we need something to practice. And my advice to you, this board is very good start. It's an excellent start for you to start practicing 4-layer simple printed circuit board. And you can download the design files in Altium Designer for this board. The good thing about ST and Texas Instruments, they have collaboration with Altium. So all their boards and reference design, they made it available and they are in Altium Designer. Just go to the resources, and under the resources, there is a schematic in here. So download this zip file. And then unzip it. Now, look at inside. So these are Altium design files, and you can find there is a PCB library and schematic library for the component used on this design. This is very good for you. So let's go to Altium Designer. Let's close all these documents. Save none. I don't want to mess up the design in here. Now for this sensor design, again, it's everything in my dissertation. But if you are thinking about commercializing this sensor, because you can build the same one, make a copy of it, make sure to read the patent application in here, and you are not gonna infringe my patent application. So there is a patent around this one, patent application, so be careful about trying to commercialize this. You can read the data, read the dissertation, try to benefit from the idea and the design. It's fine, but don't make a product out of it, because there is already product out of it and there is patent application lying underneath this. So let's go now and take a look at this before we close this session and call it a day. Okay, so basically, as you can see, this is a project for the board we downloaded from ST, and you can see the libraries in here. Let's see if anything is not added. Okay, so you can see that. So if you combine this project, it will show the nets and the components. And if you take a look at the top, as you can see, they used Hierarchical Design, and they have microcontroller, and they have ST-Link. ST-Link is basically programmer and debugger, and very simple connection, very simple project. And this is the microcontroller, and this is the programmer. So as you can see, this is the top sheet, and this is the first child. So you have a microcontroller, you have connections, connectors, power regulations, crystal oscillator. On the second sheet, you have ST-Link, programmer ST-Link 2, and you have a microcontroller which is working as programmer. It has a programming code and debugging code on it. And you have couple connectors and power regulations around and USB interface as well. It's very simple and very easy to use and design as a startup project for you. So this is the layout. This is very small board. It's really small board. So if you look at the board, it's very nice for as a good start for learning. So it has 4 layers. Let's hide all these mechanical layers, and let's hide these as well. So let's hide the components as well. Let's take a look. So on the top layer, you see we have components on the top layer, and we have also ground polygon. You see this ground polygon in here? It's everywhere on the top layer. And if we look at the other layer, you have the bottom. Also, you have a component, and also you have a ground pour in here. So they have a component and they have a ground pour, and this is very good practice to have ground pour around the signals. And let's take a look now on the inner layer, and this one is called the ground, as you can see, and everything on this layer is just the ground. And if you come closer, look at these vias, they are connected to the ground and they have a power signal. And look how they did, and this is a new design, by the way. They have sections. So this section is basically, let's click on it to see what is this about. This is 3.3 volt ST-Link. This is the power supply for the debugger and programmer. And then they have this section. This is a U5 volt. This is coming from the USB interface. And they have this section. This is E5 volt. This is like auxiliary power supply. And they have multiple power supplies on this board because you have different options. This is VO, voltage output, and then they have this. This is VDD. They have this. This is 5 volt, and they have this. This is analog VDD. And you see how they are distributing the power and making very solid connections between the points. So here, for instance, this one is U5 volt. You have 1 via, 2 via, 3 vias, and then they have 1 via in here. And they are connected with polygon or power pour. And you can see them in here. Polygon pour, polygon manager. They have 12 polygon. So this is the layer. You can sort them by the layer. On the bottom layer, you have only ground. It's connected. On the top layer, you have only ground as well. Now, on the ground layer, you have ground. On the power layer, you have all these 1, 2, 3, 4, 5, 6, 7, 8, 9 pores. And these are the signals connected to these pores. Of course, you can change them in here. You can control that and change them, change the color or hide them, etc. This is how the board. So if you want to start by learning 4 layers PCB, so during this course we practice 2 layers. We already practiced 2 layers with through-hole components and also with surface mount components. And if you want to start practicing 4 layers, it's the same thing. You just need to create power and the ground layers. In the inner layers, make sure to branch your vias. Let me show you how they branch the vias as well in here. Let's see here. So they have, you see the power is branched in here, ground is branched as well. Branched goes to the inner layer. 5 volt branched goes to the inner layer. Let me show the power layer in here. This is the power. Let me hide the polygon. Design tools, polygon pour. I need to hide the polygon on the top layer. This will make it more clear. Shelved. Okay. So here. So you see, this is about here. 5 volt goes in here. It's just a branch and connect from inside. The other one goes up here. So branch and connect inside. Branch and connect inside. They could like route it from here, come over the here and here, but this basically you are distributing the noise, the power supply noise over the whole board. You really don't want to do that. You want to get this as short as possible, connect with the inner plane, and the inner plane is very close to the ground plane, and they will help to reduce the noise of your signal and make your design very robust. So this is the general guidelines you can follow when you design for layer PCB. Now, I think that is enough for this session, and this is the last session of this series during this semester. Now I'm planning to teach signal integrity for high-speed digital circuit design in spring 2019 for graduate students. It's also 5,000 level class, similar to this one, and that one will be very comprehensive, very extensive, and requires a deep knowledge on electromagnetic fields, as well as analog circuit design, maybe some RF design. And this is coming in the spring, I hope. So talk to you in the spring semester. Thank you all, and have a wonderful